Institute at Maryland. Before Kaiqing joined Maryland, he was the postdoc at MIT, and I think you also spent 1 semester at Berkeley as Simon's Institute's research fellow. Since I know Kaiqing, he has done many interesting work in different areas, from control to decision theory to reinforcement learning to machine learning and their intersection. And his work have won many awards, to just name a few, from UIUC CC's award and to best paper award like ICML August paper award and NSF Career Award, and recently just won the Air Force YIP Award. So to just name it. So the floor is yours. Okay? Please take it away.
Right, thank you. Thank you very much. Thank you very much, Tommy, for the very nice introduction. Also, thank you very much for the invitation, and thank you for coming. It's really my great honor to be here to present to you or share with you some of the things we have been thinking about lately on this topic. So let's okay, dive in. Before I forget, this is a joint work with a bunch of fantastic collaborators, students of mine, and outside collaborators. So I'll be mainly talking about these 2 papers, a very recent work on this topic, to share with you some of our recent results. If time permits, I may mention the first one, but we may skip that if we are short on time. So a little bit background on why we are doing what we are doing. So we know that over the years, we have seen significant progress on autonomous AI agents. So applications like high-profile applications like playing Go games, or using GPT as large language model agents, or problems like problem solving, coding, and embodied AI agents like robotics, also like gaming agent and e-commerce. So when I say agent here, what I want to emphasize is that in particular, I focus on the AI models for decision-making tasks, and especially in dynamic environments. So if you really look at many of the success stories here, for example, playing Go games, many of them naturally involve multiple AI agents interacting with each other, sometimes also interacting with human beings. For example, in playing Go games, it's by nature a 2-player zero-sum Markov game or dynamic game. Like in the large language model agent example, you have a conversation that has to be 2 agents there, like a human and a GPT. Other examples include like fleet of robots and fleet of autonomous driving cars. Therefore, they have inspired many new results, I would say, recently on theoretical foundations for multi-AI agents recently. So I was always asked the question, what's really unique or what's really challenging if you really move from single AI agents to multi-AI agents? Think about self-driving car as an example. So on the left-hand side is really what happened in either a simulator or when you get an AI agent. But what's really happened is something on the right. So in my opinion, there are several unique challenges that we need to address in order to really address this multi-agentic settings. So first unique challenge here is the non-stationarity and the strategic nature of the environments. For example, other agents, which could be AI agents or humans, they are also learning and adapting. However, many AI agents nowadays oftentimes built with a single agent mindset. For example, if you think about large language model agents, they will train to pre-train to predict next token with no other agents in the mind when you try to build such an agent. Or like if you use RL to do it, oftentimes we just set up a reward and try to maximize it. So this agent will not train for handling such a non-stationary and strategic environment. So now the key issue here is that usually, if you really think about the interaction of multiple agents, the number of agents are just large. So to address the scalability issue, one remedy here is try to use some decentralized learning. For example, you can train an agent as if there's no existence of other agents. It's more scalable. However, this decentralized learning paradigm may usually make the problem even worse in terms of non-stationarity, and and it's really hard to account for the multi-agentic nature in this decentralized learning paradigm. Thirdly, is probably the focus of this talk, and I would say probably is kind of relatively less studied in the recent theoretical development of AI agents, multi-AI agents, is really the asymmetric and decentralized information among agents. For example, sometimes AI agents are trained with some privileged information. Let's say GPT was trained using the internet data, which may not be available in the training of each agent in your lab, or they may include some knowledge that not every human being has. Or sometimes AI agents are trained with a high fidelity simulator. They may contain some information that you don't have in the real world. Also, each agent, like in the self-driving car example, you may only be able to observe your surroundings, and you don't have the same experience of the information shared by other agents. That's why we want to really try to study the case where you have AI agents, but they have asymmetric and decentralized information. Okay, so the environment could either be like, you can view the environment as just some external environment, or it's just consists of multiple agents interacting with. To address this setting, in this talk, I'm gonna talk about two results. The first part is more on the more classical reinforcement learning agents. We ask and try to answer the question how to address this asymmetric and decentralized information provably. And then I'm gonna move to a more modern type of AI agents, which is large language model agents. We want to address the issue of how to better understand and even further enhance the decision-making capability with some principles we know from online learning and reinforcement, especially in the strategic and decentralized learning environment. Also, feel free to interact me if you have any questions. Let's start with the first part. Let's talk about RL agents with asymmetric information. So reinforcement learning has been, recently we have made a lot of progress in studying the theoretical foundations of RL, has been predominantly studied on the model of Markov decision process, MDPs, where the system states are perfectly accessible. But in practice, we know that usually it's not the case. Agents only have partial, noisy, or delayed observations, almost as always. Like in self-driving car example I just mentioned, or in robot learning example, where you have a camera, you can only see like a very cluttered thing, only part of the objects. How are you going to finish this manipulation task? There are tons of examples showing that partial observations are just prevalent. It is even more so in the multi-agent setting, where agents have imperfect and decentralized information about not only the state, but also other agents' information. This is even more challenging and relevant in the multi-agent setting. In theory, this is very hard. So we know that even in the single agent case, if you want to plan, or meaning I know the model exactly, I want to find the optimal policy in a partial observable setting. There are many fundamental hard results in terms of either computation or sample efficiency. Not to mention in the multi-agent case, we know that it may take double exponential time in the worst case to find a team optimal solution, even if you have only two agents. It is also NP hard to find even the single step optimal policy if you have decentralized information. Those are old results. Right? And also from a control literature, we also know that even if the system is linear, but because agents have decentralized information, the optimal policy to be nonlinear. That's what people call the Wilson-Houghton counter example. It's a very intriguing and interesting example that inspired what we study here.
So I just want to clarify a little bit. In multi-agent settings, I guess there could be setups where the agents are cooperating in some way towards a agreed upon goal, versus situations where they're not necessarily cooperating. And I guess I'm not clear where the distinction is, and then there's single agent.
Yeah.
So the team policy really suggests they're cooperating.
Yes. This hardness here is team optimal is regarding where the agents even share the same, which arguably is even easier, but still hard in the sense that you are looking for a team optimal. But another thing you mentioned is for like non-cooperative game theoretically. like agents may have even conflict of interest. But it's also relatively easier because there you are not looking for, like, for example, the summation or the social welfare is maximized, maybe just some.
Yeah.
That's relatively easier solution concept. So it depends on which one. But here is more about cooperative.
Gotcha.
Yeah.
Thanks.
Yeah. It's very nice question. So in general, what we know is that actually decision making and learning with partial observations are hard. But meanwhile, in deep RL or in empirical RL, I got a chance. I was very fortunate to talk more with robot learning people during my postdoc. So I learned a lot from them. In fact, to them, partial observable RL is not that different from the MDP formulation of partial observable RL in their experiments. So in many of the examples I mentioned here, like for example, the robot learning dexterity from OpenAI, and also learning for robotic locomotion or self-driving car, or even in this OpenAI playing Dota example. So one key algorithmic ingredient they mentioned to me was that they use good simulator. They want to make good use of what they call it privileged information they have. What do they mean by that? It means that usually a privileged information here means some additional information available only during training. It also refers to, for example, in a single agent case, the access to the state. How to make it happen? You can build a very high precision, like a high fidelity simulator, or you may have a high precision sensors at training time, so that you can have access to the state. But you don't have that in your test time. Okay? It's more even relevant in the multi-agent setting, where people use what they call centralized training and decentralized execution, where in the training phase, there's a simulator, I can collect everybody's observation for training. But at the deployment phase, I don't have that information. It's very extremely popular in practice. Give an example, in the locomotion example, this was, I believe, a work from ETH. They train robots for locomotion tasks. At training time, you have this privileged information in the simulator, but at test time you don't have that. Or in this multi-car example, at training time you have observations from all the cars, but this is what you deploy in the environment. So as shown in this figure, at training time you can collect everybody's O and A. At testing time, you only take your local O and A as input for your policy. So in other words, the final goal is unchanged. You want to learn a partial observable policy that can be deployed without privileged information at test time. So a little bit more of formalism. So we start with a very general setting, partial observable MDPs, POMDPs. So that at each step H, agents observe some OH from some, we call it emission function OH, which is just a probability distribution condition on the current state S. But you cannot directly have access to S, the state. Agent then takes some action, receive the reward, and state transition to the next state. And in general, in this case, optimal policy has to take the form in the following way, where you have to make use of the full history of the observation and action you have observed so far, instead of just using the current state, because you don't have access to them. And the goal here is try to optimize this expected accumulated reward. Okay. And this kind of go to Rob's question: how do we model a multi-agent setting? So we consider the corresponding part should be a partial observable stochastic game. In fact, it's a generalization of the fully observable Markov game or stochastic game. Most recent multi-RL theory focused on, including, Qiaoming had a very nice paper on this. I also worked on this before, this Markov game setting. This is a strict generalization of that, where agents only have decentralized and partial observation. In particular, at each time, agent I will observe by H from this emission function, and agent I will make decisions with the reward, but reward Ri could be different across agents. And then when they share the same reward function, we call it a cooperative setting. This usually some people just refer to as decentralized partial observable MDP. But we will show in next slides. There may be some difference there. But still, before that, let's say each agent I at each step try to take action from some policy. So policy condition is conditioned on the information this agent I has at time step H, which could be the whole history you have. Or in some cases, that's why I wrote here as a subset of this, because sometimes agent may share some information. That's something I'm going to talk about later. Okay, it's just a part of the whole history you have seen before. And then what you care about for each agent is that expected accumulated reward for that particular agent. Okay. In this case, we'll consider different kind of solution concept, let's say. So one typical one is equilibrium solution, where at that point, there's no incentive for this agent to deviate from that option. Depending on how this joint policy pi and minus I are correlated, either Nash equilibrium, where they are just product policies, they make individual decisions. If there are correlation among the policies, it's a correlated equilibrium or coarse correlated equilibrium. Also, I would say the holy grail here is the team optimus, which is that in the cooperative case, it's just the best policy that optimizes this expected accumulated reward. So the first idea,
J is the sum of the JI.
Usually when we talk about team optimal, we only care about for DEC from DPs.
On RI side.
Yeah, same. Yeah. Cool. So one idea we found pretty interesting was the idea from empirical RL is called privileged policy learning in order to address this asymmetric information. In particular, what that means is that in training, also only in training, you condition the policy on the privileged information. In particular, what we mean by that is that it's a very popular, actually intuitive approach that decouples this policy learning into two steps. So first step is try to learn an optimal, fully observable policy, they call it expert, or a teacher policy in a simulator. You can use whatever your favorite, MDP learning algorithms. And then what people do is that you distill that policy into a partial observable policy class. They call it a student policy. So in the locomotion in that learning paper, they call it teacher-student learning. More concretely, you try to minimize this F divergence between the pi star you learned expert policy and some pi H. Perhaps under some behavior policy to sample this trajectory, want to find such a distilled policy so that you can implement at test time. It's a very simple idea. It's also modular in the sense that this learning algorithm in the first step could be any RL or partial observable RL algorithm. And also because of that, you don't have to handle exploration issue in the partial observable environment. Okay. But does it work? Actually, we show that it doesn't. Okay. Even with relatively informative observations, doesn't in general, So you can show that actually it's not very hard to construct a POM-DP where under certain conditions I'm going to explain soon. So there's always a constant gap between the best distilled policy and optimal policy in that POM-DP. So when I say relatively informative, what I mean is by this gamma observability condition, which was a condition initially proposed in Ivan Dar's paper, and recently by Golovich et al. To show that this was a condition that can enable planning and learning in POM-DPs without computationally impractical order. It's basically saying that for any belief, if the beliefs are different, after you pass through that emission function, you should be able to differentiate them a little bit. Okay, so meaning this emission function is relatively informative in essence, but still under this condition. So what's the intuition? Why it doesn't work? So key idea is that, so this kind of example ensures that the belief given the observations is uniform over the states. However, at each state, expert policy are very different. The other thing of this example, so on the left-hand side, that's state one. So obviously, I should, as an expert policy, I should choose action A1. On state two, I should choose action A2. Because of the prior we chose for the state, if you condition on this observation of one, okay, I want to implement a partial condition on that, I compute the posterior distribution or the states is uniform. Because of that, the distilled policy, the best policy I can choose, think of a case because I don't know the state to me is very uncertain, and at each state they choose different actions. Then to me, the best distribute policy should be uniform also. But if you really compute the best optimal policy in the partial group space, you should always choose the left-hand side, because if you go to the right, you get like epsilon. On left, if you go to the left branch, you get 1. That's why you always have to suffer from this optimality gap.
One good question. So, what can you also incorporate the rewards you observe for distillation?
No, that's exactly.
But this is
when they do it, they don't. That's exactly. So that's a very good point. So the reason is because when you do that, you didn't account for reward. While the underlying state is very uncertain. Yes, exactly. Any questions so far?
So when doing the distillation, you are only allowed to use the
Expert policy.
policy, but not any other information.
Yeah, that's what people do oftentimes. Yeah. Cool. So when will it work? So one observation from this example is that the unseen state remains highly uncertain at the key, even condition on this relatively informative history. That's the reason why at least that failed. That inspires us to consider the following structure assumption, which I chose to use it more like a signal processing kind of a type of name. We call deterministic filter condition. So that means is that we say upon DP satisfies this condition, if satisfied the following. So if you maintain the filter of the state by observing like new action and new observation, if that filter is deterministic, we say this POM DP is satisfying this deterministic filter condition. In other words, if you give the current observation at first step, I should be able to, estimate state pretty well. And then as the state evolves, but also as more information come in, I should be able to estimate or track it very well. So that the uncertainty here of the state is not so high. Okay. What does this condition even mean? Essentially means that this filtered state estimate, or the latent state, is relatively deterministic. In fact, you can show that it covers several important known tractable POM DP subclasses. One example people study a lot recently is called block MDP, where basically they assume the observation is very informative, such that I can decode the state immediately, okay, in one step. Also, people study like a multi-step decodable case, L-step decodable, meaning if you have a finite memory, you should be able to exactly decode the state. They also cover, to me, as an interesting case, which is deterministic, where the transition is just deterministic. In particular, found this condition kind of interesting is that it kind of unifies several existing conditions on either the transition or the emission. Remember, in these two cases, block MDP and the L decodable POM DP, there's no assumption made on the transition. But in the deterministic POM DP, you made no assumption on the observation. In other words, there seems to be a trade-off. You think about what's really a tractable POM DP problem. You should be able to unify either like the conditions for the informativeness, like x-axis here, for the observation, or the determinism of the transition. Going either way would make the problem easier. And this deterministic filter condition is kind of unifying some of them. In fact, you can show that this condition is equivalent to show that you can use a whole history of arbitrary length to decode the state. Okay. Then under this condition, what you can show is that you can use a very simple and modular approach, which is you call your black box MDPR algorithm to get pi star fully observable. And then you use that to collect a bunch of data. And then you just try to solve, a classification problem essentially. Try to learn this decoder recursively. And on that, you can show that in a tabular setting, this algorithm can learn epsilon optimal policy with high probability with both polynomial sample and time complexity. In the case with function approximation, general function approximation, it learns an epsilon optimal policy with high probability with poly sample and the poly cost of a classification oracle, which is people believe is a tractable oracle. Any questions for the result? Yeah.
Is it just a sufficient or also a necessary condition?
Sufficient. We only show it's sufficient. Yeah, that's a good question. That's a very important future work we are considering. Yes. But still it's weaker than all the conditions I mentioned. Yeah.
Earlier you mentioned that you don't need to do the exploration. It's because you do kind of like the black box MDP server already take care of
handle it over the
exploration.
That's a point of doing this privileged learning.
So this one still doesn't cover the counter example you mentioned. That counter example doesn't satisfy this.
Yeah, exactly. It doesn't. I will assume this.
But even in that counter example,
yeah,
could tell the difference between where I am by looking at the rewards.
Yes, that's another approach, because if you look at this, right, our condition here, that's a very good point. So our condition here, like this condition, this condition has nothing to do with reward. Only about translation and omission, or it's an emission function. Similarly to all these conditions, usually we don't assume anything about reward. But I definitely believe that's another possibility to address this kind of example.
But so do practitioners use rewards when they distill?
I see some cases they distill using Q function.
Okay.
But that's kind of incorporating reward in a certain way. But we didn't study that in this teacher-student setting. That's maybe exactly doing this. Yes. We didn't study that setting. Other questions? Cool. Yeah, we can also generalize to the multi-agent setting, which a little bit trickier. I don't have time to talk today. But I guess it's like when you collect the data, you have to be more careful, because in a game setting, we care about equilibrium learning. So you really have to account for all the deviation policies for fixed equilibrium. So in other words, when you distill, you are not distilling from like a equilibrium policy. You have to fix other strategy. You have to enumerate many best response policies, like response policies, to collect the data, to learn the decoding. That's a slight difference there, but still you can get a polynomial sample and time. So how do we understand the result? What's really the benefit? So we compare with all the existing results in either learning block MDP or k-decoder MDP or deterministic POM-DP. You can show that privileged information provides strict theoretical benefits in terms of, either by relaxing certain restrictive assumptions on the transition, or you take down, like for example, in the decodable case, you can show the lower bound has to be exponential in K. How long you decode? If you go to our case, that K become H, essentially the whole H to decode. Right now, we don't suffer from that exponential dependence on the how like the decode length. Okay, it's one of the few structures assumption on POM-DP to achieve both poly sample transition complexities. Second idea we're interested in is like people also do a lot is privileged value learning. I would say this is even more popular. This is actually the algorithm got me into this topic. So what people do is that you condition the value function on privileged information only during training. So one common practice or one common example is asymmetric actor critique. In fact, that was also the algorithm used in OpenAI's learning dexterity example. So basically, you maintain a partial verbal history-based actor, which is a policy you are going to deploy later. But in training, you maintain a fully observable state-based critique, only condition on the state. So people call it asymmetric because the condition are different. So for critique, you condition the state only during training, but the policy condition on the history. And then you apply active critique algorithm. You use that Q to improve your pi and keep updating your Q. So why is it helpful intuitively? Because observation in practice can be high dimensional, like images, while states are usually low dimensional, and people believe this fully observable critique should be easier to learn. But does it work? In fact, the policy gradient of the actor for the actor update estimated by this fully observable critique is biased. Okay, so this was not first discovered by our paper. Actually, in 2022, there's another paper talk about this. So essentially, if you plug in policy gradient theorem in the POM-DP, so what's really the state you should think of? You should think of the whole history as the state. Okay, then the correct policy gradient should be looking like this. And if you only condition your Q function or the critique on the state, so in this case, in order to compute this, you have to condition this S to compute the conditional probability of tau given S to compute this expectation. That will give you a biased estimate of the policy gradient. The right thing to do is that you incorporate that tau into your Q function in addition to S. That will give you an unbiased estimator of the policy gradient. In other words, we consider an unbiased version of that. Basically, because you now have tau, first I view tau as we have seen in MDP at the state. But there's additional state there. How should I remove that state dependence? What you do is that you have to marginalize with respect to the current belief given this history. Okay? That looks very familiar to people. That's what we know, like the natural policy gradient or mirror descent in general in RL algorithm. But there are two issues to analyze or to even implement this algorithm. The first one is that you have to enumerate all the possible history. That's obviously not tractable. It's exponential in the horizon. And also need an oracle to compute such a belief, okay, which require model knowledge. For issue one, it's not that hard. In fact, the whole point of this recent work that tried to solve POM-DP is under this gamma observability assumption, you can in fact use just a finite memory of history at the state to approximate this tau pretty well. So that both your Q and pi will depend on this Z, which is a finite memory history. And also the D you only need that to be logarithmic order. For issue two was really the trouble there. So how are you gonna estimate this belief? The idea is that you want to estimate the model, like in terms of translation and observation in the simulator, because now you have that access to the state. And then you use Bayes' rule to construct such a belief. From existing result, we know that you can approximate this belief very well if the underlying POM-DP is gamma observable. This could be the case if the underlying POM-DP is observable and you are estimating your emission function very well across all the states. If you have such a result, for sure, you can plug in the result to have a good belief estimate. But the challenge here is that in MDP even, we know that some states may be rarely visited, any policy. It's just very hard to explore. You cannot universally estimate this emission function very well. You just didn't get enough samples at those states. But the key idea is that probably in terms of optimizing, finding an optimal policy, those states just doesn't matter. It just don't matter. What we do is that you carefully redirect some of the transitions and truncate those low visitation states. And the reason why you can do it is because thanks to this previous information, you can track the visitation of the state. And based on that, you redirect carefully, the sum of the low visitation probabilities, and then you truncate those states. And then you only learn the emission function for those truncated, the states after the truncation. You can show that on those states, you can uniformly and accurately estimate that emission function to make sure it is observable in that truncated POM-DP. And you'll connect that back, you use that result to compute the belief, and you'll show that it's very close to the original belief you are going to use.
Visitation is given to you as privileged information.
Sorry?
The count of the visitation is given to you as privileged information.
No, you have to explore. You have to do it by yourself.
You have to explore and then you have to remove
the downgrades. Yes, you have. Yes, simultaneously. Yes. Good question. Yeah. Other questions? So by doing that, we designed this belief learning oracle, showing that under gamma observability condition of the POM-DP, there exists an algorithm that can learn approximate belief function with both poly sample and time complexities. And because of that, you plug it into the belief weighted asymmetric, the correct version of asymmetric active critique, you can show that you can get a poly sample and a quasi poly time complexity in terms of computation. But that's not improvable, given the previous paper, Golovich et al. You can also generalize that to the multi-agent setting with equilibrium learning.
So yeah, what about the original bias cases? So can you do you have results that show that with bias gradient, policy gradient? And
we haven't analyzed that, but I guess eventually there will be some bias term appear in the bound, I guess. Yeah, we didn't even bother analyzing that. Yeah.
So that's very interesting. So I guess all the previous asymmetric integrity methods were based on this in-state queue.
Yeah. I wouldn't say all. Some of them maybe, yeah.
So do we actually see some gains over there if we
you mean theoretically or?
Yeah, empirically.
Empirically, actually in that paper I mentioned, 2022, that was actually a kind of half theory, half empirical. They have some more careful comparison and showed why this bias can be bad. Yeah, but algorithm is very different from our case. We haven't implemented this algorithm to compare with that algorithm yet. So such guarantees of polysample and quasi-poly time at the same time haven't been made possible without privileged information before. The best people can do is that you can have quasi-poly sample and quasi-poly time on this model. But there's improvement if you do that with privileged information. But still, it's still open that whether you can achieve the same kind of result without using privileged information. I think that's in general still open. Yes, for a long time, I have a second part to talk about. I'll probably very briefly mention this. So previously, I mentioned two ideas I learned from DeepRL, from robot learning people. There's actually another idea I found it pretty interesting. Was some idea from control theory, from decentralized stochastic control, which is people call information sharing or partial history sharing. So key idea is that I quickly mentioned this. So we just showed that decentralized learning and partial global learning in multi-agent setting is pretty hard. So when is that less scary? Especially, let's think about the case where you don't have privileged information. In fact, that's a topic people study a lot in control theory. They actually classify different information structures. Basically, depends on who knows what and when. This kind of characterization. They also generalize that to the game theoretic setting. There's some very nice work from this literature that shows that you can actually formulate a dynamic programming problem on this common information space. Okay. So these are just some examples. Especially it can be used to handle the case where you have some delay in the system, which is very common in multi-agent control systems. But what we want to study is that how this information sharing may help sample and computation in RL, in multi-agent RL. So what we show is that actually you can solve this problem first of all. Those works they didn't study learning first of all. In fact, you can show that both observability and information sharing are kind of necessary if you want to solve this multi-agent RL problem. And under observability and a certain amount of information, you are able to show a quasi-polynomial time and sample complexity for this multi-agent learning problem. So here I just want to show you, how useful maybe, or how useful the idea from decentralized stochastic control could be in this learning setting. And there are definitely more we can do. Any questions so far for the first part? Great. So this now brings me to the second part. So we also are very interested in this, the decision-making capabilities of LLM-agent. So there are some initial exploration we did in this domain. So we know that there has been some excitement, or I would say hypes of large language models, caused sensations across academia, industry, and society. And some of the work even show they saw the sparks of AGI because of that. And with many fantastic application domains. People have been increasingly use LLM as an agent. So when I say that, what I mean is that they use that for decision making. Okay. So basically they use LLM as a brain or the central controller of the decision making. And then you could either call some other tool, or you could either use some other agent to help you in this multi-agent setting, and then interact with the environment, get feedback, and keep doing that. One inspiring example of this work was actually a very, I would say, super interesting work from Percy Liang's group at Stanford. They call it generative agents. What they did is that they built a sandbox with, let's say, 25 agents. They play in different roles, simulate, human behavior. They interact with each other. They repeatedly interact with each other and intervene the plan of the days. What they claim is that there are some social behavior naturally inferred. For example, the diffusion of the information. Let's say one of the agents said, I'm going to throw a party on a particular day and spread the information. And on that day, people just, team up and show up for the party. Okay? There are also some other social behavior they observe, let's say the coordination among the agents, or the agents just naturally form a relationship with each other. They said that's a believable simulacra of human behaviors. But to me, what's really interesting is that, first of all, is or why an agent for decision-making is even a good idea or reasonable idea. And the second question motivated by that generative agent paper is that how to really quantify the emergent behaviors when you have multiple such LLM-agent interactions. So I like simple models. If you really think about this interaction process, what's the simplest canonical model we can think of? So we started with an online learning problem. Okay? This problem has a deep connection to game theory and equilibrium computation, I'll mention briefly also. In particular, I guess many of us must be familiar with this already. So an agent interacts with the environment for T rounds, choosing a policy based on the history at each time T. It commits to a policy, and then incurs a loss. And then you'll have to take the product between the loss and the policy you're committed to. And then you receive either like the full vector of that loss vector, which is called full information setting, or sometimes you only get access to one particular realized loss for the action you have taken. It's called, people call banding, let's say. They repeat this process for multiple rounds. So I view that as a very canonical and I would say overly simplified setting of a sequential decision making in this case. So what's a good metric in this case? So typical wise, people use regret or just external regret. If you think of an algorithm or an agent, so it measures the difference between the accumulated expected loss by implementing this agent and the accumulated loss incurred best in hindsight. Okay? So this is a definition. Why that's important? So a reasonable agent should be no regret, some people argue. In the sense that by saying no regret, what it means is that you make this regret to be sublinear time. Okay? It can be used as a way to quantify or evaluate the level of rationality of this online decision maker. Are they good online decision makers? Are they making sense in this decision-making process? It can also be used to measure the robustness against arbitrary or adversarial environments. Because the law sequence I just mentioned, people don't make assumption on how the losses are generated. It's a non-stochastic or even adversarial setting. And also, I would say more interesting to us is more on the game theoretic setting. If you have multiple such agents, if all the agents are no regret, we know that they can lead to some equilibrium. In this case, correlative equilibrium. And that learning process is kind of decentralized. Okay? You just run your own copy of the no regret algorithm, and the equilibrium will just emerge. And finally, we also saw some empirical evidence people have done to use this no regret model to predict human strategic behaviors, to really justify the importance of being no regret learners. A quick, very quick background on this. So in order to be no regret, there are several features of this learner. Probably the most typical one is what people call the follow the regress leader. So you take into account a history of the loss sequence, and the minimum one, but up to some regression on this term to make sure the output is kind of less predictable. Another very closely related algorithm is what we call follow perturbed leader. Has kind of the similar flavor, but it's the randomized algorithm, where I accumulate a loss, and then I add a random perturbation on this accumulated loss. And then I'll just pick the best action. But the key idea is that using either regularization or random perturbation, you are able to make yourself less predictable. And also you look at the whole history so that you're not very greedy to the instantaneous loss you receive in order to be no regret. So the question of interest here is that, are they good decision makers in this very canonical model with this very canonical and standard metric? So we did some experiments. It's a very fun experiment. So we experiment on several representative IM at the time. It's very, things are moving very fast. So interaction protocol is as follows. So H is for human, A is for agent. So each time with human, we'll describe the route to the agent. So you are playing, like you're making decisions for P rounds. At each round, you need to choose a policy based on the history, let's say. And then could you return me a policy? As if you're asking the LLM agent to make decision in context. Okay. And then we will design the loss. Human will design the loss. Here's the loss vector. Give me the policy, and I repeat. And eventually, we will track the regret as defined before. I hope this setup is clear. It's very simple setup. In the game setting, so we human are moderator. So you just report me your policy or strategy in that case. Then I will marginalize with respect to the payoff matrix, and then give your marginalized like payoff vector back to each agent. Okay? And use that for your own decision making.
Just one quick clarification question. So here, do you consider full information feedback or banded feedback?
Full information. Most of these are full information. Yeah. And then we'll track the regret. In the online setting, how we generate loss, we consider either like randomly generated losses, and also we consider like some losses with trend. We also have an extension to the like more non-stationary and banded settings, and also sometimes we don't give the numerical one. We just use a language to describe the loss, but that's a little bit trickier. But in this experiment I'm going to show, we use this very numeric loss vector. We generate losses in the online setting in these particular ways. In the game setting, we use either the representative games, which contain these 5 examples from the literature, which people call the representative enough to model the strategic behavior of multiple agents. And also, we also have many randomly generated games in this case. So what we show is that actually, at least to me, I didn't expect this. So it's kind of cool to see that I'm making some decisions. Okay? They can be no regret. And sometimes they achieve even lower regret than FTRL, FTPL. And overall, GPT series are better and more reliable than those open source ones. That's what we have seen in this in many of the examples I mentioned. In the game setting also, in this case, the adversary or the other opponents are less adversary because they are also no-regret learners. They are also LLM agents. They are less adversary. So regret performance are even better in that case. And also, a little bit interesting is that we asked the LLM to explain what's going on. So we see some of the explanations are kind of interesting. So they need to look at history. We don't know where they learned that actually. They knew they need to look at history. So that's one feature we know from FPRL. You shouldn't make detection only on the immediate loss sequence. You should look at history. And also sometimes they even say something like, oh, they want to be less predictable, or they want to introduce some randomization in their decision. Or sometimes the randomization just comes from the fact that it didn't compute the probability correctly. But there is some randomization in their output. Okay? Yeah.
For the 4-player game, Like each LLM agent sees the other's policy, is it?
No, we don't. We just give them the payoff vector. So we are human doing the marginalization. Let's have a payoff matrix 2 by 2.
So they never learn to either cooperate or be adversarial to each other. Like there is no incentive of doing that.
Sorry?
I mean, they have no incentive to be like cooperative or adversarial
No, yeah,
to each other.
fully decentralized learning.
Fully decentralized.
Yeah. Like typical online learning or learning game setting, where all the agents are just neural learner. They don't even know, there is an agent.
You say, for example, that right now we don't want to choose our action based on what is happening right now because you want to motivate a TRN. I buy that.
Yeah.
But also mirror descent that does the lazy mirror descent that does something for the instance that we look. It is also not good.
I see. Yeah, that's
like I'm trying to understand. Is it so correct that if I am focusing on, like, my claim is that there are other methods of learning, such that even if I see my feedback right now and I react acutely to the feedback that I see, also it's a no regret process. So I don't believe that this is the reason not success of the model, but
yes. I agree with that. So I guess you are saying that first of all, there are many ways to achieve neural graph, or in that sense, I would say neural graph is not that hard to achieve in general. Okay.
Right.
But what we want to connect to, although it's, as I will mention later, is super hypothetical. We don't know what's going on inside, so it's super hypothetical. So what we looked at when you look at example, what came to our mind is like this kind of two features. Okay, that really matters. And also, hopefully, we can make some sense of it later. Yeah.
A clarification question. Okay. So you are doing in-context learning. So at time t, you are giving like till t minus 1, what is my loss vector?
Yes, I give them.
So why is it so? It has to look at the history. Like why?
Yes. So, because sometimes they exactly. Not surprising. I wouldn't say it's surprising. It's just what we observe. Okay. Because sometimes they compute the average. If you ask them to explain the compute average, I know it's also not that surprising, but that's to me. When I first saw it, it's kind of interesting. Okay, so they look at the history, they take average, and then they introduce randomization, things like that. But let me get to the in-context one pretty soon. That's exactly the point. But still, I want to make it very clear. So it's definitely not in general. You can easily fail it. Okay, easily achieve fail to be neural graph. But what's kind of interesting is that I want to mention is that we first started with, we want to say, how can we fail it? Okay? We start with the case that fail follow the leader. Okay? We know it's like on the left. Essentially, it's alternating loss. If you fail on the first step, you'll fail. You get linear graph. But in fact, if you input this loss to LM, they can easily succeed. Okay, but that's also kind of intuitive because the pattern is so obvious. In fact, they can know the pattern, they can infer the pattern, and then they can do a good prediction. But if you add a little bit noise onto that, they would fail. They would achieve linear graph, like on the right, because noisy alternating loss. And also, if you are more adaptive, of course, they will fail. So these are the figures to show how they fail. If you have a noisy alternating loss or like adaptive, in this case. If in the cases they succeed, what's really the very hypothetical explanation for this? How to really think about this? Our process is highly hypothetical. So the idea is that this trained LM may mimic certain neural algorithm, of course, under some assumptions. So under several assumptions, including, for example, the training, which in this case is either in the pre-training phase or in the supervised fine-tuning phase, is a next token prediction. You predict like the next token. If you assume the function class you are using to do this maximization is large enough, and also there are like infinite number of samples so that you can compute the expectation. And also in this data, we include the optimal action of some decision. Okay. And also some Gaussianity assumption on this data you can show from this figure give us maybe a better illustration. So basically, in this case, you can view this X as a prompt that are describing the loss sequences. Okay, and you can use that to infer what's really the loss sequence L1 to LT. And you can use that to further infer the latent thing or the concept in the in-context learning case. But in our case, it's a latent task you're trying to solve. And then if you have this optimal action in your training data, you'll get a Bayesian inference process such that the posterior distribution given all this L1 to LT will exactly be this probability, which corresponds to follow the projected leader. In particular, we make exactly that point. We want to connect that to the recent Bayesian kind of perspective understanding of in-context learning, where we really view these loss sequences as context. So a quick note is that for those who are not super familiar with in-context learning, basically I give you some context, like say London, the UK, DC, the USA. Then if I ask Beijing, what's up? So you know that's like China, for example. If you look at this loss sequences as an input, as a context, and then I'll use this to infer what's the underlying task. And then if you have the optimal action in your training data, you can show that the posterior distribution exactly corresponds to the output of the follow-up leader. So that's kind of the hypothetical explanation we had why it kind of works and connect to FTPR and in-context learning. Any questions for this? I guess I'm running out of time. Let me quickly mention the last part, which I think is even more, I would say, more interesting, is that can we even further promote the neural graph behaviors of these agents? Because it makes sense, because these agents were not trained for decision making, right? They're trained to predict the next token. How to promote this neural graph behavior especially without this optimal action in your data? We propose a new training loss we call regret loss. So basically, the idea is that if regret is really the metric you care about, how about let's try to minimize the worst case regret? But in the inner loop, you have a maximization. You have a minimization on the outer loop. This is pretty hard to optimize. So we propose some surrogate that essentially you penalize the regret by square it, by randomly sample this loss from some symmetric distribution, and then I minimize the following loss. So you square the regret, and then you take expectation over the randomization of your loss, how your loss are generated. And then I just train on this loss, or train transformer on this loss. So what we show is actually, in terms of optimization, you can also establish some statistical guarantees for that. But what we found interesting that you can show some optimization guarantees, meaning if you focus on one layer transformer to get some insight and minimize that particular loss, you can show that the stationary point of the regret loss I just proposed, with some projection, the output has to be projected on the L2 ball, will perform for the regress leader with L2 regression. And when you have one layer linear self-attention models, meaning the global minimum of that regret loss will give us FTRL if you have this projection. So basic idea is that the key insight here is that you sample L following distribution I just mentioned. Minimizing that square loss will lead to the output in the following. Because the L's they are just symmetric, so I'll put the same weight on all the L's. So that's become a summation of that. That's going to be my output. If you additionally do a projection, that gives us back FTRL. So that's the idea of how we make one layer transformer will work in this for this regret loss minimization.
One quick question. So what about if you just look at the original loss with the simple transformer setup? Maybe you had before.
Oh, that's for which what's the loss? It's a decision making problem. How should I formalize the entropy loss, cross entropy loss?
Oh, I see. But
so we want to design that for this online learning setting.
It's very useful. Well, I can basically not give.
But we don't want to. But you don't really signal.
You can think about the sequence of actions yours.
Yeah. But which action? Optimal action or from some algorithm?
Well,
we don't want that actually. We want to avoid labels.
let's say I see. Okay, so it's difficult to specify the policy.
Exactly.
Yeah. But let's say if you just choose a random policy doesn't, and if you choose the random,
Yes.
see generate the sequence of agent actions everywhere. First.
Yeah.
If you just learn extra prediction from that, then you. I'm not sure what will help.
That's a very good question. I think people are doing that. They call it algorithm distillation. So if you get the labels from some algorithm, in this case, policy is also an algorithm. Build that as output of some algorithm, then probably they will mimic that algorithm.
The random.
Exactly. So that's the, which may not be a good policy here. Yeah. Sorry, I'm running low on time. Let me finish. So I guess we trained that lot on one layer and multi-layer transformer using that new loss we proposed. Actually, these are the performance they have on the typical, like regular losses we mentioned. But I think more interesting is that we actually also train that and then use that to address the regrettable cases that LLM failed, like the adaptive ones and the noisy ones. So, like, I think it's kind of hidden here. It has much better performance than the big models. So to quickly conclude, I guess AI models are increasingly deployed as agents interacting with the world, with each other, and with humans. So principled and fundamental different thinking is required for building AI agents in such multi-agentic and strategic environments, especially with asymmetric and decentralized information, including new fundamental limits, new types of guarantees, or new metrics, new losses, a new data collection process, as I mentioned. So along this line, we have two attempts. One is to address classical RL agents. We get insights from both deep RL and control theory. They can help sample and computation provably. Although you have to be very careful when you try to deploy those insights. For the LLM agent, we try to provide more principled understanding and controlled understanding with new training laws that promote the decision-making capability. But still, I want to emphasize, I'm not suggesting this is the right way to solve online learning on games. You shouldn't use LLM to do that, nor is the right way to use LLM in practice. Because just try to get a little bit more understanding of what's really going on for this LLM agent in decision-making. It's just our, very initial exploration and fine exploration. And definitely we pose more questions than we were able to solve. Finally, I guess there are many open questions. On the theory side, there are definitely more questions regarding the understanding of the interplay between information and RL efficiency. For example, how to get tighter upper and lower bounds for both sample and computation capacity. I think right now, many RL theory results focus on sample efficiency. Okay, but I guess it's very important to consider both sample and computation efficiency, especially under some new condition we had and under different information structures. Or in general, let's say impartial over RL, what's really the minimum information or minimum representation for you to get efficient learning. And also, right now, we are trying to scale up this training of this regret loss or other decision-making driven losses on actual language models, try to make the algorithm more amenable to decision-making tasks. This requires new algorithms and new data collection pipelines, and also other new metrics from either online learning or RL to promote such decision-making behaviors. And that concludes my talk. Thank you.
For the nice talk, given the interest of time, let's take the question.